Take a look at the magnetic ordering of an iron bar, the chemical bonds holding together a molecule of water, and the outward pressure sustaining a dying star. From a classical perspective, these appear to be three completely separate physics problems, governed by different macroscopic forces. But classical models fail to explain their existence. In magnets, for instance, classical magnetic dipole-dipole interactions, the actual magnetic fields generated by individual atoms, are thousands of times too weak to maintain spin alignment against thermal energy at room temperature. A single quantum mechanical rule, the exchange interaction, is responsible for the structural stability of these systems. To see how this ordering works, we have to scale down past the atomic lattice, looking solely at a single pair of overlapping electron clouds. We are going to discard classical physics entirely and build the exchange energy from first principles. We only need three concepts to build this model: the absolute indistinguishability of electrons, the symmetry of quantum wave functions, and the electrostatic Coulomb repulsion of negative charges. Mapping the mathematical interplay of these three concepts is the only way to derive the Heisenberg model of magnetic ordering. We begin with a foundational axiom of quantum mechanics. All fermions of the same type, like our two electrons, are absolutely identical and completely indistinguishable from one another. Because they lack any individual identity, mathematically swapping the spatial positions of electron 1 and electron 2 cannot result in any measurable change to the physical properties of the system. To satisfy this condition, quantum mechanics imposes a strict mathematical rule. The total wave function describing a system of fermions must be antisymmetric upon particle exchange. This antisymmetry requirement is the formal mathematical origin of the Pauli exclusion principle. It is a rigid structural mandate that permanently restricts how electrons are allowed to distribute themselves in space. An electron's total quantum state consists of two properties linked together: its physical location in space and its intrinsic spin direction. We express this by stating that the total wave function, psi, is the product of the spatial component and the spin component. Because the total wave function must remain strictly antisymmetric to satisfy the Pauli exclusion principle, the symmetries of the spatial and spin components are inversely coupled. If the two electrons have parallel spins, a symmetric triplet state, the mathematics force their spatial wave function to be antisymmetric. Conversely, if the electrons have antiparallel spins, an antisymmetric singlet state, the math allows the spatial wave function to be symmetric. Spin is a purely abstract property, yet flipping its direction acts as a toggle switch that reconfigures the electron's spatial reality. An electron's spin direction strictly dictates the physical geometry of where it is mathematically permitted to exist. We can translate this mathematical symmetry directly into physical geometry, starting with the antisymmetric spatial state caused by parallel spins. In an antisymmetric spatial state, the wave function crosses through zero precisely at the midpoint between the particles. This creates a mathematical node where the probability of finding an electron drops to absolute zero. This zero probability node physically forces the electron density clouds outward, increasing the total distance between them. We see the exact opposite geometric behavior caused by anti-parallel spins. Lacking this central node, electron probability merges directly between the nuclei. Now we apply our final variable, electrostatic Coulomb repulsion. Both electrons carry a negative charge, meaning they naturally repel one another. Forcing the electron clouds apart in the parallel spin configuration reduces their electrostatic repulsion compared to letting them merge together. This results in a significant drop in the system's overall energy, creating a dominant ordering effect that functions independently of any external magnetic field. There is a precise mathematical difference in energy between the overlapping anti-parallel configuration and the separated parallel configuration. This chart shows that specific gap between the high-energy anti-parallel state and the low-energy parallel state. We define this delta mathematically as the exchange integral, denoted by the letter J. We formalize this into the Heisenberg-Hamiltonian equation. H equals negative 2j times the dot product of the two spin vectors. The dot product serves as a mathematical sensor for spin orientation. It calculates whether the vectors are aligned or opposed, allowing the equation to assign the correct energy state based on the spatial symmetry we just arrived. Under this convention, a positive J value means that parallel spin alignment minimizes the system's energy. A negative J value dictates that antiparallel alignment is the lowest energy state. The Heisenberg model proves that indistinguishability, spatial symmetry, and electrostatic repulsion combine to generate an effective organizing pressure. When we scale this interaction up from an isolated pair of electrons to a three-dimensional crystal lattice of billions of atoms, we see macroscopic results. In materials like iron or nickel, the exchange integral is positive. This forces massive domains of electrons to lock their spins in parallel to maintain the lowest possible energy state. This vast, forced quantum alignment is what generates the macroscopic magnetic fields of the permanent magnets we use every day. But in materials like manganese oxide, the exchange integral is negative. This forces the spins into a rigidly alternating up-down checkerboard pattern known as antiferromagnetism. Because this perfectly alternating order cancels itself out locally, the resulting crystal lattice possesses high structural order but generates zero net macroscopic magnetic field. The macroscopic properties of these materials depend entirely on the sign of their microscopic exchange integral. We see this exact same mathematical constraint scaling horizontally into molecular chemistry. To form stable covalent bonds, atoms share electrons in an overlapping symmetric spatial state between the nuclei. Because the spatial state is symmetric, the NAF requires the shared electrons to possess antiparallel spins, and the effect scales up to the level of astrophysics. When a star exhausts its fuel, unyielding gravitational forces attempt to crush the remaining matter into a singularity. As the matter compresses, the Pauli exclusion principle and the resulting exchange forces generate a rigid outward degeneracy pressure, physically halting the collapse of white dwarfs and neutron stars. The exchange interaction is an absolute architectural constraint. Because matter is indistinguishable, its mathematical symmetries are locked. That purely abstract quantum rule dictates the precise geometry of chemical bonds, the physical existence of magnetic fields, and the structural survival of stars.